After examining all the individual aspects of a rational function, we're ready to put it all together and construct a graph. So let's look at the procedure and all the details we have to think about in order to create a detailed graph of a rational function. Number 1, identify the domain of the rational function. Number 2, locate the vertical asymptotes. Don't forget, the form for the equation of a vertical asymptote is x equal to c. Number 3, we'll locate the holes if they exist. And remember, holes are expressed as an ordered pair AB. Number 4, locate the horizontal asymptotes. The equation of a horizontal asymptote is y equal to a constant. And then number 5, write the equation of the slant asymptote if it exists. The form for the equation for a slant or oblique asymptote will be y equals mx plus b. Number 6, we'll look for the x-intercepts by solving the rational function r of x equal to 0. The form for an x-intercept will be some constant followed by 0 as an ordered pair. Number 7, the y-intercept of the graph can be obtained by evaluating r of 0, and the ordered pair will be 0c. And then finally, number 8, we'll sketch the graph including all asymptotes and holes. We'll label each asymptote with its equation and important points with ordered pairs. And then for the big finish, we will double check our graph with the calculator. So that's a lot to think about, and we're going to go through all of those steps on each function on example 7. So follow that process to graph the given rational function. So on example A, we have the function f of x equals 2x squared over x squared minus 9. When we're working with rational functions, we certainly need the zeros of the denominator, and those are more easily identifiable if the denominator is factored. So let's factor that denominator as x plus 3 times x minus 3. So at this point, we need to observe there are two restricted values. That is, zeros of the denominator. X cannot be equal to negative 3, and x cannot be equal to 3. This gives rise to our domain. In interval notation, our domain would be from negative infinity to negative 3, union, negative 3 to 3, union, 3 to infinity. Notice from the original function that neither of those factors from the denominator are removable. That is, we can't cancel them out. For that reason, they lead to vertical asymptotes. So where our domain is divided, we're going to place in the graph a vertical asymptote. So I'm just going to abbreviate these VA for vertical asymptote. They have the equation x equals negative 3 and x equals 3. So in this case, both of our restricted values led to vertical asymptotes. Remember, sometimes they lead to vertical asymptotes, sometimes they lead to holes. Now, I like to keep up with all the information as we go. So I'm going to go ahead and come over here to the graph and sketch our vertical asymptotes. One at x equals negative 3, and one at x equals 3. Because there are no removable factors that create the 0 in the denominator, I'm just going to make the note there are no holes in this graph. Next, we want to locate horizontal asymptotes. Don't forget, we get horizontal asymptotes by examining the relative degrees of the numerator and denominator. So notice the degree of the numerator is 2, and the degree of the denominator is 2. So in this case, our function has equal degrees in the numerator and the denominator. So if you remember our mnemonic device, Bobo Botten eats dog chow. This is the eats dog chow case. We have equal degrees, so we're going to divide coefficients. That is leading coefficients. So for a horizontal asymptote, the form of the equation is y equal to a constant, and we're going to find the ratio of leading coefficients. So the leading coefficient on top is 2, and the leading coefficient on the bottom is 1. So the ratio 2 divided by 1 gives us the equation y equals 2. So let's go ahead and sketch that on our graph. We have the horizontal asymptote y equals 2. Now, because we have equal degrees and an oblique asymptote requires the degree of the numerator to be exactly 1 more than the degree of the denominator, we can observe there are no oblique or no slant asymptotes for this rational function. So the asymptotes have divided our grid up into regions. Now we need to locate some specific points on the graph. Let's begin with x-intercepts. Now remember, to find the x-intercept, we set y equal to 0. And y is the same thing as f of x. So we're going to set our entire function equal to 0. Now, if you're paying attention here, there's a little shortcut that you can observe for finding the x-intercept of a rational function. To solve this equation, I need to multiply both sides by that denominator, x squared minus 9. Every single time you set a rational function equal to 0, and then you multiply both sides by the denominator goes away. So the shortcut here is to find the x-intercepts, you can simply set the numerator equal to 0. So solving this by dividing both sides by 2 and then taking the square root of both sides, we get one value, which is x equal to 0. So putting this information together in an ordered pair, we found x equals 0 when we set y equal to 0. So our x-intercept is the origin. So we know the graph is going to cross the x-axis at 0, 0. Also notice the x-intercept is coincident with the y-intercept. If you weren't paying attention, just to give you a demo here, to find the y-intercept, we set x equal to 0. So notice we would have 2 times 0 squared over 0 squared minus 9, which would give me 0. So that would give rise to the same point. So we're ready to sketch the graph, but we only have one point on the graph. One thing that we could do would be to choose x values. Maybe I could take x equals -4, x equals +4, plug it into the function and find other ordered pairs on the graph. But instead of doing that, I'm going to make use of the calculator. We've got the main details of the function ironed out, that is the asymptotes, the intercepts. So now I'm going to use the calculator just to observe the general behavior of the graph. So let's get it typed in here. We can verify our asymptotes. So remember, we found x equals -3. I can see it right there. X equals 3. Our horizontal asymptote was at y equals 2. And we can also observe our x-intercept is 0, 0. For the rest of the graph, I'm just going to sketch the general behavior. So we have a little small piece up here. We have a little small piece up here. Again, just general behavior. And our graph does something like this. Observe that we have 3 branches to the graph. Note how that fits in with what we came up with the domain. We said the domain is going to come in 3 intervals, and in this case we have 3 branches to the graph. So the specifics that you want to include on your rational function, the location of the asymptotes and their equations, the intercepts labeled with ordered pairs, and the rest of the graph will sketch the general behavior using the calculator. Okay, that wasn't so bad. Let's take a look at another example. So example B, we have the function g of x equals x minus 1 over x squared minus x. As always, we need the zeros of the denominator. So let's go ahead and factor it by extracting the GCF of x. And that leaves behind an x minus 1. So observe, we have a removable factor here. That's important to recognize. And our function reduces to 1 over x. But before I look at my reduced function, I want to look at the factored form because this is what represents the original function g of x. And I'm going to observe there are 2 restricted values, 2 zeros in the denominator, one from this little factor, x can't be 0, and from x minus 1, the 0 there is 1. So our 2 restricted values are 0 and 1. We are going to exclude both of those from the domain. So our domain would be from -infinity to 0, union, 0 to 1, union, 1 to infinity. To distinguish between wholes and vertical asymptotes, we have to pay attention to, can we cancel the factor or not? We canceled that factor x minus 1. So you can think of it as we removed that factor from the rational function. Remember, a removable factor goes with a removable discontinuity or a whole. So we know the whole is going to occur at the 0 of that removable factor. So our whole occurs when x is equal to 1. But remember, we got to find the y value. So how do we find the y value of the whole? Well, we look at our reduced fraction. If we plug 1 in for x, we would end up with 1 over 1 or 1. Be ordered pair 1, 1. I'm going to jump over here and plot that point on the graph. Remember, it's a whole, so sketch it as an open circle and go ahead and label it with its ordered pair. Now, the other restricted value, x equals 0, came from this factor, which we can't cancel out. That's a non-removable discontinuity, so it gives rise to a vertical asymptote. The equation then would be x equals 0. Remember, the equation for a vertical asymptote is always x equal to a constant. So let's sketch that on our graph. Next, we look at horizontal asymptotes. The skill is totally different for finding a horizontal asymptote than a vertical asymptote. Remember, we look at the relative degrees of the numerator and the denominator. So the degree of the numerator is 1. The degree of the denominator is 2. So it's bigger on the bottom. This is the Bobo case. So we would say the horizontal asymptote occurs at y equals 0. Remember, Bobo stands for bigger on bottom 0. So we'll have a horizontal asymptote right on the x-axis. Because the degree of the top is not exactly 1 more than the bottom, we do not have any slant, also known as oblique asymptotes. No oblique asymptotes. All right, discontinuities have been covered. Let's talk about intercepts. To find the x-intercept, we set y equal to 0, or we set the function equal to 0. Now, if I did this with the original function, I would have 0 equals x minus 1 over, in the factored form, x times x minus 1. Notice, as we observed before, that's going to cancel our common factor, and so our function reduces to 1 over x. This equation has no solution. That is, there's no value that we could plug into the denominator to make that equation equal to 0. So this particular function has no x-intercept. The same is true for the y-intercept. We find the y-intercept by setting equal to 0, x equal to 0, and once again, if we plug 0 into our reduced function, we have an undefined fraction. That simply means there is no y-intercept. So the graph of our original given function g of x is going to resemble the graph of 1 over x, except we're going to have a hole in the graph at x equals 1. To visualize the graph, or observe the general behavior of the graph, I want to type in the original function, not our reduced function. So we had the function x minus 1 divided by x squared minus x. So we can observe our vertical asymptote is correct. Our horizontal asymptote is correct. It nicely fits the curve. But what we can't see on the graph is the hole at ordered pair 1, 1. Although it's not visible on the graph, it will be available if we look at the table. So if you'll type second followed by that table button or the graph, observe when x is equal to 1, it tells me the y value is an error. So there is a hole there. It's just so small, it's 1 pixel big, that the calculator doesn't show it very well. And we can also see when x is equal to 0, there's an error. That corresponds with our vertical asymptote. So we can go ahead and sketch our graph. Both branches are going to follow the vertical asymptote and the horizontal asymptote. And even though we had 3 intervals in our domain, we only have 2 branches to the graph. The first interval from the domain, negative infinity to 0, describes the location of this branch. The middle interval, 0 to 1, describes from the vertical asymptote to the hole. And the final interval from 1 to infinity describes the rest of the graph. Okay, let's try one final example. We have h of x equal to x squared plus 1 over x plus 1. It appears that we have a single restricted value from the denominator, that is, x cannot be equal to -1. Also observe the numerator is the sum of two squares, so it does not factor. The domain of this function will be from -infinity to -1, union -1 to infinity. So our domain comes in two intervals. We'll expect two branches to the graph. Now, that restricted value, x equals -1, comes from a non-removable factor in the denominator. Because it's non-removable, that gives rise to a vertical asymptote. So the equation of our vertical asymptote would be x equals -1. Let's go ahead and sketch that on our graph. We want to sketch it and we want to label it with its equation. Since there are no removable factors, we can observe there are no holes in the graph. For horizontal asymptotes, we observe the relative degrees of the top and the bottom. The degree of the top is 2 and the degree of the bottom is 1. So we have the bigger on top case. Remember, if it's bigger on top, there are no horizontal asymptotes. So we have no holes, we have no horizontal asymptotes. However, did you notice that the degree of the top was exactly 1 more than the bottom? So we will have an oblique asymptote. OA, oblique asymptote. Remember, you can also call those slant asymptotes. Now, to locate an oblique asymptote, we need to divide the top by the bottom. So I'm going to use synthetic division. I'm going to put the 0 of the denominator in the box, and we'll put the coefficients of the numerator on the first row. Don't forget, with synthetic division, we have to have a representative of every descending power. So the first coefficient I have there is 1. That represents 1x squared. There's no x term, so I'm going to insert a placeholder, 0, and there is a constant term. So once again, this is my x squared term, this is my x term, and this is my constant term. We'll skip a line. We'll bring down our first number, and then we multiply the number in the box times the number on the baseline, and then we add vertically. So number in the box times number on the baseline, and add vertically. Remember, that last spot is our remainder, and it's not part of the equation for our oblique asymptote. So we started here with a degree 2 polynomial. After one round of synthetic division, we have a degree 1 polynomial. So this represents my x term, this represents my constant term. So the equation for our oblique asymptote then would be y equals 1x minus 1. That's in the form mx plus b. So let's sketch that on our graph. So we'll observe, first of all, that the y-intercept of our oblique asymptote is at -1, and the slope is 1. So I'm going to go up 1 and right 1 to make another point on that line. And then we can connect the dots with a dashed line. And our oblique asymptote has equation y equals x minus 1. Let's locate intercepts if they exist. So to find the x-intercept, we set y equal to 0. So we set our entire function equal to 0. And as we mentioned before, the shortcut is just set your numerator equal to 0. Let me remind you why. If I multiply both sides of this equation by that denominator, it's going to cancel on the right and leave a 0 behind on the left. Now, notice in this case, if I solve this equation with the square root property, I'm going to get plus or minus square root of -1 or plus or minus I for x. Imaginary values don't show up in the real plane, so how do we interpret this? This simply means there are no x-intercepts for this graph. Let's see if there's a y-intercept. The plan for finding a y-intercept always is to set x equal to 0. So if we replace all the x's in the original equation with zeros and simplify, we end up with 1 over 1 or 1. So we do have a y-intercept at ordered pair 0, 1. So we'll go ahead and plot that. Now, although I have a pretty good guess about the graph looks like, let's observe the general behavior of the graph by examining it on our calculator. So we'll type in the original function, x squared plus 1 divided by x plus 1. And we can observe our vertical asymptote here at x equals -1, so that's correct. But I'm going to go back to y equals, and I'm going to have the calculator graph my oblique asymptote as well. So I'm going to type in y equals x minus 1, and it will graph it on the calculator in red. So we can see that both asymptotes fit the curvature of our graph. We can also observe our y-intercept there at 0, 1. And so we can sketch that in by hand. Both sides are going to follow the asymptotes, not plotting specific points there, just looking at general behavior. Now notice there's 2 branches to the graph corresponding to the 2 branches to our domain. So there's a lot to think about. You want to locate restricted values, use those to find your domain, find vertical asymptotes, locate holes if they exist, horizontal asymptotes, oblique asymptotes if they exist, x-intercepts and y-intercepts. But remember, the calculator is tremendously helpful in looking at the overall pattern of that graph.